So just a quick note, if you were here on Sunday for the extended version of this paper in the Plan Rob workshop, by all means feel free to go for lunch a little bit early. There's quite a lot of overlap between this and the first portion of that presentation. Might be optimal. So we're very proud to be here at ICAPS presenting our work on finding ways to get the job done. Now, I'll get straight into it. In a perfect world, our own plans as humans are short, they're quickly made, they're simple, and they always go just as we expect them to. That's perfect. Reality is a very different picture, and it's actually very insightful because despite of this, or in spite of it, we still manage to find ways to get the job done. So if you look at how we actually do it, it's by adapting to the environment, like all animals, right? So if, for example, we want to drink some water and there are no clean mugs or no clean glasses, we have no problem whatsoever using something else, right? So we substitute objects. We substitute actions. If we find a box, we try to lift it, it's too heavy, we have no problem with pushing it along or asking someone to come help us. So we find ways to get things done. Moreover, we even take advantage of opportunities that will allow us to make our plans shorter or simpler, right? This is really admirable. Getting things done is very important for us, right? And we want to do it perfectly. Yeah, we teach our kids to do it perfectly, but in the end, we care about getting things done. So we have no problem satisficing in order to get it done. And the reason this is good news is because if we can manage under the conditions that reality imposes on us, then maybe we can find a way to get our robots and our agents to do the same. And that's the motivation behind us, because for robots, it's exactly the same as us, actually. Even with incomplete information and everything, just the same as us. So our approach to do this is by combining affordances, planning, and description logics. So affordances are really just opportunities for action, right? And by focusing on functional affordances in particular, we're trying to make use of all this information that we've learned over history about cups being used for drinking from and chairs being used for sitting and so on and so forth. And we also, really reduce our action space at the same time. And we then use HTN planning to actually encapsulate the procedural information about how we should go about executing our tasks, so we have that. And then we're using OWL-DL, which is form from description logics, a language in description logics, and we represent our domain in this formalism and our functional affordances. So all our objects, their functional affordances, their parts, and the functional affordances of their parts as well, all of this is represented in OWL-DL. And in addition, we actually also represent the methods and the operators of our planning domain, right, of our planning. And this should allow us to infer the relevant parts of the domain and to find substitutes when needed. Right, so if we quickly take a look at when the problems actually come up, well, they could come up, you could fail to generate a plan for numerous reasons, and you could also fail to execute one, right? So for example, it might just happen that you forgot to model an instance of a kettle, or you actually have no kettle in your new apartment, right? You haven't unpacked it yet or something. So it happens, you'd fail to generate a plan. You might have teacups, but they're all dirty, so you'd fail to generate a plan that, to make tea or something. You might not know if you have milk or not, right? And all of these are reasons why some plans may never come to fruition. So also during plan execution, it might happen that you did everything properly, you localized properly, you navigated properly, and then once you get there, the kettle isn't where you expect it to be, right? It happens more often than not. So the first step is actually not to go ahead and plan. The first step is actually to model the domain, right? Everybody, we know how hard it is. This last couple of talks showed exactly this. And in our case, obviously, if you want to make tea, then you have your methods and your operators, and you're all ready. And then you'd give it, as humans, we'd prepare the problem perfectly. We know that we only care about kettles, about the locations of the kitchens, and about the teacups and what have you, and we provide all of this nice and neat and give it to the planner to plan. The alternative is to give it absolutely everything that we have about the world, not just this intentional knowledge, and then just wait and wait and wait and wait for the solution to be returned. So our old colleague, Ronnie Hatanto, for his thesis, came up with this idea of combining HTN planning and description logics reasoning. And this allows us to use then really powerful off-the-shelf reasoners that are available to infer relevant parts. And the way he does that is for each method and operator, he explicitly specifies which part of the description of the world is relevant. So if you want to use this particular method, what do you need to know about the world? So then we can go ahead and create this focused planning problem that includes just the intentional knowledge that we expect. And to do that, you have a task is given, then you have a problem generator that will actually go through and query the knowledge base and hopefully get as the answer all the methods and the operators that decompose this particular task. And because it's a hierarchical approach, you know exactly which methods and operators might be used in the process. And then you have this focused planning problem in OWL-DL format, and you still need to transform it into a format that the planner will use. And that's something we're currently working on. Now, hopefully you generate a plan, you might end up with something very nice and short, and you did it quickly, and everything works nicely. I'll just quickly draw your attention to a couple of things. So last year when we presented this, we showed how we're actually providing for a manipulation component, for example, the reason the object is being grasped, for example, because it differs. If you're grasping something to pour, it's going to be a different grasp than grasping something to transport it, and so on and so forth. And this is something we did last year, and this year as well. Now we've extended that to navigation, so that we want to be able to tell them, you're going to this place in order to grasp the kettle, so make sure that the destination pose that you pick is reasonable. Right, so let's pretend that we have a particular decomposition for making my own tea. And I like to use my own teacup when I drink my tea. And let's pretend that in this particular case, it's dirty or missing or something. So we have a problem. We might fail to generate a plan, full stop, and go back, and there's nothing to be done. But we want to do something different. We want to make substitutions. So we go back and we expand the domain and create a new planning problem. And we do it as follows. So we've modified the planner slightly so that it creates an extended plan, which I'll go into a little bit later, but also this plan generation failure explanations. And this basically might tell you, I could not generate a plan because there is an unmet precondition, blah, 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 in branch this of this particular method, and what have you. And then, because we're operating under the open world assumption in OWL, we know that the difference between something being unknown and something being plain false, right? So we know the teacup is either dirty, or we have no idea if it's clean or dirty. And in the case that it's unknown, then we want to be optimistic. We're just going to say, okay, update the knowledge base. You have a clean Iman's teacup. Go ahead, produce the plan, and go and execute it. And if we have a problem, we'll deal with it then. Otherwise, if it's dirty, then it won't work. So we know for a fact it's dirty. Then what we want to do is lift our plan to use an alternative object. And last year in PlanRob, we presented a flexibility ladder, if you will, someone called it, along which you climb. So, for example, in the first case, it called for a particular instance to be used. This is not available, so let's expand this choice of alternative objects and use any common instance of the same class, so any old teacup. And again, here we would prefer things that are closed. This is something we do to be more efficient, right? We prefer closed things. Next, you'd climb up and look for other objects with the same functional affordances, so for drinking from, that happen to be conceptually similar. And conceptual similarity is something else that we use a lot. So other things that might be small, bowl-shaped containers with a handle. And then you keep relaxing these constraints. So you might end up with a flask or a bottle, just things that are conceptually similar, and things that are, most objects used for drinking from tend to be small, cylindrical containers made of glass. And you're probably thinking, there is no way I would ever find it okay to drink my tea from a jar. You're absolutely correct. And but if you look at other uses of objects, and on Sunday I said, well, what about storing stuff, right? Normally you finish eating, you have some leftovers. You wouldn't mind storing it in a teacup, I don't think, if you have run out of bowls or Tupperware containers. So it depends on the task. And obviously, for safety reasons, for usability, and for improved performance, what we do is the agent should always ask and confirm. And what it's actually offering is basically a preferences over choices. So, hey, I couldn't find this. May I use this or this? And the agent, well, the user has to say, yes, no, I would prefer that you did this or whatever. So you go around, you generate a plan. Now we have a grounded plan with a proper instance, you go ahead and you try to use it to act, and this is how we act. This extended plan is just the regular actions within your plan plus the grounded add and delete lists to make it easier for the execution monitoring component to update the knowledge base every time it's acting based on the feedback it gets from the state. So was this action successful? Was it monitored to be successful? Validated in this case, yes or no? We also have updates to the knowledge base every time you perform a sensing action. So, for example, in a continual planning setting, you might want to tidy up a room. You don't know what things might need to be tidied up beforehand. So you drive to a location, you take a look, you update the knowledge base, and now it knows, okay, there's a jacket on the back of that chair which I need to tidy up and everything else is okay. And you continue. So it triggers a plan generation problem. Now at execution, the same thing might happen. You drive there, you thought it was there, but it's not. So the kettle is missing. And now you can actually go ahead and expand the domain as we did before to include substitutes. And I made it seem very easy the first time around and said, okay, we lift, and lifting is fine, but it's not sufficient, right? So I'm not responsible for this, by the way. I found this on the web. So the thing is, it's not just enough to substitute for the variables of the new instance, but you have to also include in the expanded domain all the object-specific procedural knowledge. So I'm not using an electric tea kettle anymore. I might be using a regular kettle or a pot, so I need to include all the methods that allow me to boil water in one of those. And then you can go ahead and generate a plan, hopefully, that uses these methods, execute it, and hopefully, despite everything that reality throws at us and our limited sensors, by combining affordances, planning, and description logics, these robots can actually find a way to get the job done. So thank you.
Okay, questions?
Yes, so there's some work long back by Richard Altman on adaptive planning,
yes,
which reminded, some of the things that you're saying reminded me of that, and are you aware of it? Or?
I'm actually not, no.
Okay,
what
you may want to
name?
look at
I need
Richard Altman, Altman and
Altman,
adaptive
okay.
planning. And this sort of, I mean, he also does, I think his example is if you know how to navigate, like, subway in San Francisco and you're suddenly stuck in New York, how do you do it?
Yes.
And, so I think you might find it interesting.
Yeah. Thank you. Thank you very much.
Okay, other questions? So I have some general AI question related to Michael's talk in the morning. He showed that sometimes reinforcement learning can generate surprising behavior of the agent, surprising to the developer of the agent. So did you observe something similar here, or everything was exactly as you expected?
It's a very good question. So we're still implementing the system. Parts of it are more implemented than the other parts. But that is exactly what while we were doing thought experiments, if you will, to see, okay, what would we need? What would be a good test case? What would be a good use case? And that's exactly what happened, actually, including things like this. And yes, using not just kettles, but boiling. And it links nicely. On Sunday, somebody brought up the idea of, I brought up the idea of hierarchical goal networks, which I know one of the students now is also working on, and he's here. And this fits very nicely with the functional affordances, because we're talking about boiling and all of this, so it links perfectly. So now to do it that way, hopefully it makes it a little bit more tight. But yes, thank you.
Okay, so if there is no more questions, thank you again. And that's the end of the session, so see you in the afternoon.